Assalamualaikum and a very good morning to all of you. We are from Group 4 and today we will present to you about the Fluidized bed reactor. But before that, let me introduce to you to our group member. The first one is Yasira binti Yusuf. The second member is Anisofia Ishak. The third member is Tengku Intan Nur Zahira binti Tengku Hussein. The fourth member is Wan Nur Afika binti Rasidi and the last member is Nurhani Shafi'i. And then we will proceed with the next presenter that will present about the introduction of the fluidized bed reactor. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Tengku Intan Nur Zahira binti Tengku Hussein. Okay, so before we go further, let me introduce to you guys what fluidized bed reactor is. First of all, it is known as heterogeneous catalytic reactors in which the catalyst is fluidized within the reactor. It is widely utilized in food and chemical industries and chemical processes where the major design parameters are diffusion or heat transfer. It also consists of gas-solid, liquid-solid, and gas-liquid-solid three-phase reactors, which are more effective for increasing the mixing and heat transfers. Next, the extensive mixing in all directions for this reactor give results of excellent temperature stability and increased mass transfer and the rate of reaction. It also has the capability of handling large amounts of heat and catalyst. Lastly, the solids or catalytic particles are supported by an upflow of fluidizing fluid, which means fluidization occurs when small solid particles are suspended in an upward flowing stream of fluid. This reactor also provides easy loading and removing the catalyst. This will be very advantageous when the solid bed must be removed and replaced frequently. Next, I will explain about the working principle of fluidized bed reactor FBR. Firstly, before the reactor is started, the catalyst pellets lie at the bottom of the reactor. The reactants are pumped into the reactor through distributor continuously, causing the bed become fluidized. As you can see in this diagram, the distributor is here and the reactants will be pumped from here into the reactor. The bed's behavior after initial fluidization depends on the state of the reactant. If it is liquid, the bed expands uniformly with increased upward flow of the reactant, and this is called as homogeneous fluidization. If it is gas, the bed will be non-uniform because the gas forms bubbles in the bed, resulting in aggregative fluidization. During this process, the reactants react due to the presence of the catalyst pellets, forming products that will be removed continuously.
Next, I will explain about fluidization regimes for suspension flow. My name is Yasira binti Yusuf, 118279. Okay, most systems experience a range of flow regimes as the velocity of flow rate is increased. So, as you can see here, the pictures of fluidization regimes. It is increasing the velocity from left to right, which is the most left one is the lowest velocity, and the most right one here is the highest velocity. And for bubbling, slugging, and turbulent, it is aggregative fluidization, which means that the reactant is gas and the bed will be non-uniform. Why? Because gas will form bubbles in the bed, so the expansion will be non-uniform. Okay, next, further explanation about fluidization regimes. The first one is fixed bed, applicable for gas or liquid reactants with low velocity. When a fluid is passing upward through a bed of fine particles at a low flow rate, the fluid merely seeps through the void spaces between stationary particles. Here, the picture shows the void spaces are very small and the reactant just passes through these void spaces at low velocity. The second one is minimum fluidization for gas or liquid. At a still higher velocity, a point is reached where all the particles are just suspended by the upward flowing gas. As you can see in the picture here, the void spaces between the particles is larger than the one in fixed bed. The third one is smooth fluidization applicable for liquid only. A limited increase in gas flow rate above minimum fluidization can result in smooth and progressive expansion of the bed. Uniform expansion occurs and no bubbles are observed. As explained by Intan just now, if the reactant is liquid, the bed expands uniformly. The fourth one is bubbling fluidization, applicable for gas only. An increase in flow rate beyond the point of minimum fluidization results in large instabilities with bubbling and channeling of gas. As you can see in the picture here, the bubbles are formed in the bed. Next, slugging fluidization for gas. The gas bubbles merge and grow as they rise up, and in a deep enough bed of small diameter, they may eventually become large enough to spread across the vessel. There are two types of slugging, which are axial slug and flat slug. Slugging normally occurs in long and narrow fluidized beds. As you can see in this picture, the fluidized bed is quite narrow than the others, and you can see there are two types of slugging here. Then the next one is turbulent fluidization. This is often regarded as a transition regime from bubbling to lean phase fluidization. Particles are fluidized at a sufficiently high gas flow rate. The terminal velocity of the solid is exceeded. Thus, the upper surface of the bed becomes more diffuse, and a turbulent motion of solid clusters and voids of gas of various sizes and shapes occurs. Here, the picture shows the various sizes and shapes of the void of gas. And the last one is lean phase fluidization for gas and liquid. As the gas flow rate increases beyond the point corresponding to the disappearance of bubbles, a drastic increase in the entrainment rate of the particles occurs, such that a continuous feeding of particles into the fluidized bed is required to maintain a steady solid flow. Okay, so I think that's all for fluidization regime for suspension flow. To conclude here, the fluidization suspension flow depends on the flow rate or velocity.
My name is Wanar Afika binti Warisidi, metric number 1182319. I'm going to talk about fluid cracker FCC. For the introduction, in the world of oil refining, fluidized catalytic cracking is absolutely the heart of the most high conversion refineries today. Its development in 1942 genuinely has given great impact to the world. FCC units were in operation at 400 petroleum refineries worldwide as of 2006, which is about one-third of the crude oil refined in those refineries is processed in an FCC. So the main purpose of the FCC unit is to convert high boiling petroleum fraction to high value transportation fuels such as gasoline, jet fuel, and diesel. High boiling petroleum means that the heavy hydrocarbons, which are converted to light hydrocarbons. Heavy hydrocarbons, as you all know, it contains lots of carbons in an alkene. When the carbons is a lot in an alkene, it requires high energy to break the strong intermolecular forces between them. So this is the diagram of a typical fluid catalytic cracking unit in a petroleum refinery looks like. This is a diagram shows the detailed component of the FCC, which comprises four principal component system, which include a reactor, this is the reactor, regenerator, flue gas system, which is supposed to be here, and the fractionator or a distillation column. In the FCC unit, heavy hydrocarbons from crude oil are cracked into smaller hydrocarbons, and that's how the name cracker exists, and which then be processed into gasoline and other fuel products, which is here. The fractionator and then produce gasoline like gas oil, heavy gas oil. Okay, next, let's move on to how does FCC works. Okay, first, heavy hydrocarbons are first enters the reactor and then mix with the catalyst and then are converted into lighter hydrocarbon vapors as they travel up the reactor. At the top of the reactor, which is here, the lighter hydrocarbons are separated from the catalyst, then flow to the main distillation column, which is the fractionator. So this reactor is using the concept of a fluidized bed reactor. Okay, next, the catalysts that are separated from the lighter hydrocarbons will fall down to the side of the reactor through a slide valve to the regenerator. During the reaction, a layer of carbon, or known as coke, forms on the catalyst. The air is added into the regenerator so that the coke produced is burned off. We want to burn off this coke because the coke may inhibit the progression of the process by binding to the catalyst. Okay, next, the catalyst then move back to the reactor through a valve and the cycle is repeated. Okay, lastly, the burn of coke creates flue gas, which is in here in the regenerator. So it creates flue gas that flows out the regenerator and enters the equipment ESP. I suppose the equipment should be here, which is ESP is electrostatic precipitator that function to remove any small catalyst particles using static electricity. Okay, so for a better understanding of how the process works, let's have a look at this. is about 2015 explosion at ExxonMobil Refinery in Torrance, California. This is basically a summary of the explosion incident. The explosion occurred in the refinery's fluid catalytic cracking, which is FCC unit, where a variety of products, mainly gasoline, are produced. A reaction between the hydrocarbon and catalyst takes place in what is known as the hydrocarbon side of the FCC unit. The remainder of the FCC unit is comprised of a portion of the reaction process and a series of pollution control equipment that uses air and is known as the air side of the unit. It is also determined that on the day of the incident, a slide valve that acted as a barrier failed. Then the failure of the slide valve allowed hydrocarbons to flow into the air side of the FCC. It is critical that hydrocarbons do not flow into the air side of the FCC unit, as this can create an explosive atmosphere. Lastly, the flowing hydrocarbon was ignited in a piece of equipment called the electrostatic precipitator, or ESP, causing an explosion of the ESP. We also provide you a video regarding this incident so that you guys will understand more about this incident.
The sequence of events that eventually led to the explosion at the refinery began on Monday, February 16, 2015, when a piece of equipment in the air side of the FCC unit, called the expander, vibrated forcefully enough that the refinery's control system automatically transitioned the FCC unit to a standby mode known as Safe Park. During Safe Park mode, the flow of hydrocarbons into the reactor is turned off. The flow of air into the regenerator is also stopped. The two slide valves connecting the reactor and regenerator are closed to ensure a catalyst barrier is maintained. Steam is then forced into the reactor to prevent hydrocarbons in the main distillation column from flowing back inside. The ESP remains energized during Safe Park. One slide valve, however, had eroded over 6 years of operation, and even though it closed, it could not maintain a catalyst barrier in the reactor. Within 7 minutes of the unit going into Safe Park, all of the catalyst in the reactor fell through the slide valve into the regenerator. A direct pathway was created for hydrocarbons to flow between the reactor and the regenerator. But the pressure of the steam flowing into the reactor as part of Safe Park mode was high enough to prevent hydrocarbons in the main column from flowing back inside. With the unit in Safe Park mode, operators attempted to restart the expander several times, but were unable to do so. Refinery personnel met to identify a strategy to repair the expander and bring the FCC unit back online. Operations personnel predicted the expander could not restart because catalyst had likely accumulated inside. On Tuesday, February 17th, a meeting took place involving a group of refinery personnel. The group discussed a similar expander outage that occurred in 2012, for which the refinery had developed what is called a variance. A variance is a management-approved deviation from procedure. The group decided to use the 2012 variance, which allowed a departure from the typical requirements for isolating the expander. Part of that process involved installing a blind in one of the expander's outlet flanges. On the morning of Wednesday, February 18th, ExxonMobil maintenance attempted to install that blind, but were unable to do so because steam was escaping through the open flange. Steam from the reactor had traveled through the leaking slide valve into the air side of the FCC unit. Using the variance as a guide, the flow of steam into the reactor was decreased in an attempt to reduce the amount escaping from the expander. But the variance did not evaluate whether this flow rate was sufficient to prevent hydrocarbons from flowing into the reactor from the main distillation column. And unknown to the operators, light hydrocarbons from a separate unit had flowed through a leaking heat exchanger into the main column, increasing pressure inside. With the flow of steam reduced and less pressure in the reactor, nothing could prevent the hydrocarbons from flowing back from the main distillation column. The hydrocarbons flowed into the reactor, where they escaped through the leaking slide valve into the air side of the FCC unit. At 8:07 a.m., a maintenance supervisor working in the FCC unit received an alarm on his personal hydrogen sulfide monitor, warning him that hydrocarbons were leaking nearby. By 8:40 a.m., multiple workers around the expander received the same alarm, and the FCC was evacuated. In an attempt to mitigate the problem, a supervisor ordered the flow of steam to the reactor to be increased, but it was too late. A flammable hydrocarbon mixture was flowing through the air side of the FCC unit and moving toward the ESP with its multiple ignition sources. There, the flammable hydrocarbon mixture violently exploded.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurohani binti Syafi'i, and for my part, I will briefly explain about the application of the fluidized bed reactor. First application is the oxidation of the naphthalene to the fatty anhydrate, and usually it will use a vanadium pentoxide V2O5 as a catalyst, and it is at the 350 until 380 degrees Celsius. This process was first practiced in 1944 by the William in the USA. The next process is the roasting of the sulfide ore. This process is heating of the sulfide ore to a high temperature in the presence of air and to produce metal oxide or free metal. For example, for the zinc production, we will use this process to produce the zinc. And the next application is the coking of petroleum residue. And this process will produce a petroleum coke which has a coal-like material, and it has other uses in the electric power and also industrial sector. And the fourth is the calcination of the limestone, and this process is involve the decomposition of the carbonate ore, which is the limestone, and also removal of the carbon dioxide. During this process, the limestone will heated at a high temperature in order to remove volatile substance, and also it also will oxidize the limestone. And the last application is the removal of the perchlorate and chlorinated solvent from the groundwater. And this process is take place in the NASA Jet Propulsion Laboratory. The system also can remove perchlorate from up to the 350 gallons of the groundwater per minute. And in this is the picture of the FBR Fluidized bed reactor in the industrial. I think that's all from me. I will pass to the next presenter. Thank you.
Bismillahirrahmanirrahim. My name is Ani Sofia binti Ishaq 1182289. I will represent the advantages and disadvantages of the fluidized reactor. Firstly, the fluidized bed operation permit one to easily add or remove the catalyst from the reactor or the regenerator. From this picture, we can see there is the distillator, fluidized bed reactor, and the regenerator. So between this and this, there is a valve here and a valve here. The valve here will control the reintroduce of the catalyst from the fluidized bed reactor into the regenerator, and then the catalyst will use again and flow here, go through into this valve, and then use react with the reactant and produce a product, and the cycle was continuously happen. Next, the possibility of the continuous regeneration of the catalyst particle automatically at a very short time, which is the reactant and the catalyst will produce a product. So of course, when the product is produced, the catalyst will be regenerated. This happen at a very short time and continuous. Next, the fluidized state of the solid allow the reactor to operate in an isothermal manner with uniform distribution of temperature. It means that usually the reaction for fluidized bed reactor is exothermic reaction. So of course it will release heat. So the mechanism of fluidized bed reactor itself, or the fluidization lead the isothermal condition, and the temperature was same at all parts in the reactor. Thus it will lower the risk of hotspot and runaway and thermal instability that may be lead to the serious problem. Next, more efficient contacting of gas and solid than in other catalytic reactor. This is due to the fluidization process itself. Okay, for these advantages, firstly, the operating and maintenance cost is expensive and costly because we need to consider the labor cost, because we need to hire the qualified and knowledgeable engineer or chemist to handle the reactor. And also we need to consider the additional of other equipment or electronic devices to help the fluidized bed operation. And maybe we need and of course we need to have maintenance to make sure the fluidized bed reactor whether it's good or not, so it's very costly. Second, regeneration of equipment for catalyst like regenerator, expander, ESP is also very expensive because we need additional equipment to help fluidized bed reactor, because this reactor doesn't come alone in industry, and sometimes it a must to ensure the safety and the efficiency of the production. Next is the erosion of pipe and reactor internal via abrasion caused by the particle can occur. The erosion sometimes because of the high temperature or maybe high pressure, and also like the previous slide, the accidents was caused by the valve. The valve was eroded. So that's why we need to have maintenance to ensure that all the equipment in a good condition. Number 4 is the entrapment of solid particle necessitate the installation of device like a cyclone for separating and recycling fine. This is a cyclone, and this is the fluidized bed reactor, and after the product was formed, the catalyst will regenerate and fall into here, and the catalyst will move here. So this cyclone is also the additional equipment for fluidized bed reactor. Like I said, it's a must. So I think for a fluidized bed reactor there is many additional equipment. And number 5 is this reactor cannot use catalyst that will not flow freely or tendency to agglomerate, which means accumulate. When the accumulate, it will sometimes it will block the way of this, or maybe it will block the expander and cause the accident. Lastly, the iteration breakout of catalyst pellet due to the impact against reactor wall can occur. Breakout, which means the fragmentation of the catalyst that will make the catalyst to lose their active side, and maybe the catalyst deactivated, or maybe the catalyst was not work efficiently as before, and we need to introduce new catalyst. I think that's all for disadvantages.